Okay, so now we're going to talk about how to implement a Memoizer cache using FutureTask. And this particular implementation will show how we can use the Memoizer to cache function call results and return cache results for the same inputs. So the Memoizer that we implement here uses FutureTask to ensure a computation only runs once. And the computation we're concerned about here is doing the actual function call to compute the value associated with the key. So let's kind of talk through this. And first I'll show you the overall structure of this class. And of course you can get the source code here in my GitHub repository. So Memoizer is a Java generic. It implements the function interface that allows us to be able to transparently use the Memoizer anywhere function would have been used. And functions gets used a lot for computations. And internally it uses a concurrent hash map. And as you all know, this map associates a key with a value. And in this case, the value is a future. So that's pretty funky. And we'll talk more about that. And this will give us a sense of understanding how FutureTask gets used in a second. So we're mapping keys to futures to values, not keys to values. Well, it is a value, but it's a future to a value. And we use this future, which will be a FutureTask, to ensure that the long-running function, which we'll talk about in a second, is only called a single time. So here's the function, and the function is set when the user passes a function into the Memoizer's constructor. So that's how things get initialized in the first place. So here's the key, here's the apply method. Apply, of course, is going to be implemented, or it's implementing the functional interfaces apply abstract method. So here's the concrete implementation of that. And you can see it takes a key of type K, generic type K, and it returns a value of generic type V. So it's looking something up in the cache. That's the way to think about that. So here's where things get really interesting. The first thing we do is we come along and we use our concurrent hash map and we say, hey, please get me the value associated with this key, if there's anything in there. Because it might be the first time in which case there's nothing in the map yet. So we call get, and this whole thing is being used to protect against the case where multiple threads all call get at exactly the same time on multiple cores with the same key. So if that's the scenario, multiple cores, multiple threads, multiple calls to get, multiple keys that are the same value, the same key, every one of them, we want to make sure that we only call the function one time. All right, so that's the scenario. So this is going to use concurrent hash map features that were available in Java 8. And so we're first going to take a look at how you do this using concurrent hash map, and then we're going to talk about some other things. Okay, so we go ahead and get that value. That'll come back with something. Now, what'll happen if we're looking up a key that doesn't yet exist in the map, then null will be returned. So the way that get semantics work in the concurrent hash map is that if there is nothing there, then you get back a null. So if a thread, remember there could be multiple threads that are calling this apply method at the same time, or the ComputeValue method at the same time. If that's the case, then they're all going to start out by getting nulls. So when that happens, then the ComputeValue method is called. And again, there's only going to be, all these threads could end up calling ComputeValue because they all could get null at the same time. So let's go ahead and take a look. We'll take a look at ComputeValue in a second. That's where the secret sauce is of this stuff. But what you get back from this call will then be passed to GetFutureValue. And that's going to return the value of the future, potentially blocking until it's computed. So this is important, and we'll come back to this. It's a little subtle. So what happens here is the first thread of, let's say, there are 4 threads. They all call get on the cache, on the concurrent hash map. They all get back nulls. They all call ComputeValue. Only the first thread that gets in there will run, and all the others are going to block. So the first thread in will not block, but all the other threads will block. So everything except the first thread is going to block, this thread will not block because it's going to go ahead and do the computation, the only computation. All right, so just keep that in the back of your mind. So here's ComputeValue. So what this does is it takes the key and it computes a value associated with the key, and it returns a future task that's associated with it. And this is really, really, really cool. So what it does is it calls it goes ahead and it makes a new future task, and the future task is going to have a callable. That's what this lambda expression says. It's a lambda callable. And it says, go ahead and apply the key to the function, or apply the function to the key and get a value back and store that value in the future task. So this, remember, this is a lambda. So that means it doesn't actually run yet. It's just saying when this thing runs, that's what I want you to do. Then what's going to happen here in just a moment is if it turns out it really, in fact, is the first time in, then we're going to have this thread explicitly run the run method on the future task. And of course, that's going to run in that thread, and it's going to do the computation that was passed in here. So when run is called here, that is the lambda callable that will be invoked to do that work. Then what's going to happen, so that comes a little bit later, but right now we're focusing on, we make a new future task, and then all the threads will all call PutifAbsent. Now notice that all the threads will end up making a future task. So we can't actually prevent them from making the future task. They'll have multiple future tasks, but only one future task will get run. And so what's going to happen then is we call PutifAbsent. And what PutifAbsent does is it tries to atomically add future task as this guy here, as the value that's associated with the key. And this is what's called an atomic check then act operation. So this particular atomic check then act operation will make sure that only one of all these threads actually ends up doing this operation. So it does PutifAbsent. And what that says is, if it's the first thread in, then it will put the future task in the map under this key, but it'll return null. So because the previous value is null, but only for the first thread in. The other threads will get a non-null. So what happens here is if the future equals null, that means we're the first thread in. We then go ahead and call run on the future task. So this particular task will run. The other threads are blocked. And then we go ahead and return the future task. So otherwise, if we were not the first thread in, but we were some subsequent thread, then that's going to return the future that came back from PutifAbsent. And that future will be a future to the future task that was put in by the first thread that came along. It's very subtle. So now what happens is we called get here, future was null, we call ComputeValue, we get back a future, and then we call GetFutureValue. And we'll see what that code does in a second. But what that's going to do is it's going to get the value of the future blocking until it's computed. So the first thread in won't block, but all the other threads will block until the first thread finishes running the long-running computation to initialize the future. So here's GetFutureValue. It's really very simple. What it does is it will call get on the future, and for the first thread in, get won't block because it will be initialized by that point. But for all the other threads that come along that got nulls, that didn't get nulls back, they all got futures back, the call to future will actually block here until that first thread's computation finishes running. So just to reiterate this, the first thread in won't block because it's off doing the computation. Well, it'll block for the computation, but once the long-running computation is done, it'll then continue on. It will not block here because it's finished. And the other threads will block until the first thread completes the computation. All right, so that's quite a bit to contemplate, and it's rather subtle. And so that's why using FutureTask is very valuable to help implement this.